All right, today we are talking the other part of describing our graph's properties. Yesterday we talked about domain and range. So we were looking at pictures, talking about the domain and range. Today we're adding the rest of the properties, talking about the x and y intercepts, whether a function is even or odd, and whether it has any type of symmetry, x-axis, y-axis, or symmetry about the origin. These 2 days are going to follow us throughout the semester. That is going to be something we will continually ask once we look at each different type of function throughout the semester. What are these properties relative to that type of function? So being able to identify these is going to be big for us. Some reminders of things that we come in here already knowing. Finding a y-intercept. Okay, over the years you guys have found y-intercepts. Remember what that means. Y-intercept, the word intercept, where does it hit? The y-axis. How do we find it algebraically? We plug in 0 for x. And the little hint I will give you is you will have at most one y-intercept. If it is a function, you cannot have more than one. Okay, so at most one y-intercept. You do not have to have a y-intercept. But if you have one, it can only be at most one. Zeros are where it hits the x-axis. And how would we solve for it algebraically? It says plug in 0 for y and solve for x. Another way of describing that would be to set it equal to 0 and solve for x. Kind of saying the same thing. You can have multiple zeros. Just like your y-intercept, you don't have to have a 0. Most of our functions do have both of these things, but you don't have to have either. At most one y-intercept, multiple zeros possible. So, identifying them. I'm going to ask you to talk about these in one of two ways, by the graph or algebraically. So the first part, given this function y equals x squared minus 4x plus 4, it says find the y-intercept. I want you to just look at the graph to do this. Okay? So to find our y-intercept, we're going to look at our graph. When it is the y-intercept, we look at our y-axis. I'm going to trace up my y-axis until I run into the graph. And I run into the graph right there. That would be my y-intercept where I hit the graph. Typically, y-intercepts are given as an ordered pair. It's always going to be 0, comma, whatever number we ran into our graph at. And we ran into our graph up there at 4. Verifying algebraically, the way, just like I said on the last page, the way we are going to verify algebraically is we are going to plug in 0. And when I plug 0 into my function, I should get the same answer that I just saw in the picture. So let's go with f of 0, plugging in 0. 0 squared minus 4 times 0 plus 4. 0 minus 0, 0 plus 4 is 4. And those two numbers should match right there. That's verifying it algebraically. Finding our zeros. This time we are going to look at the x-axis. Okay? So as I take my pencil and trace it along the x-axis, any place my graph hits the x-axis is going to be a 0. Now remember, there can be more than one of these, so I would go all the way across. Just finding one doesn't necessarily mean we're done. So here's my x-axis, trace my pencil along the x-axis, and I will hit my graph. Now this time I only hit it at one place. A lot of times, zeros are listed as x equals whatever number we hit that at. You can list it as an ordered pair. That is completely fine, but you are also able to just say that it happens at x equals 2, and that is completely fine to do. And then the whole verify algebraically. So again, making a note for myself, what does that mean? That means I'm going to set the equation equal to 0 and solve for x. Guys, that's exactly what you did in our warm-up when we found the numbers at the bottom of that. That's the same thing as finding zeros, setting it equal to 0 and solving for x. Okay, so I'm going to set this equal to 0. Now I see x squareds, x's, and plain numbers, which means I need to either factor or quadratic formula to find my answer. Hopefully it's factorable. Factors of 4 that add up to -4. Our options would be 1 and 4 or 2 and 2. 2 and 2 works, right? -2, -2. Set anything that has an x equal to 0. And it gives us two answers, but they're the same answer, right? And it's the answer that we just confirmed, x equals 2. Any questions on that process? All right, I'm going to let you try this one on your own, just like we did. Look at the picture to find it. Use your algebra to confirm it. All right, let's start with our y-intercept. Again, I'm going to trace down my y-axis to find where I run into my graph. So as I go down the y-axis, I run into the graph right here, which would be the point 0, 0. Verifying it, I plug in 0 to our function. 0 cubed minus 0 is 0. Verified. The zeros of our function, I trace along my x-axis. And again, there can be more than one. So as I go down my x-axis, I start out and I run into my graph right here at an x value of -1. Keep going. I run into my graph again right there at 0. Add that to my list. And then I keep going and I run into my graph one more time here at +1. So it looks like we have 3 zeros in this function. Confirming it algebraically, I set my equation equal to 0 and solve. So I'd have 0 equals x cubed minus x. That again is like one we saw earlier where we would need to factor out the GCF to start this one. They both have x's. That's a GCF. Factor that out. And what's left over is a difference of two squares. I need to keep going. X plus 1, x minus 1. And then everything that has an x gets set equal to 0 at this point. X equals 0, x plus 1 equals 0, x minus 1 equals 0. And we can verify all three of our answers, 0, 1, and -1 right there. Any questions on the y-intercepts or zeros? Jordan? You can list the zeros as just a singular number, or if you want to write all of them as ordered pairs, you're welcome to. Just don't get the order wrong. But y-intercepts we always write as an ordered pair. It wouldn't be a function. And so we're not going to really see graphs like that. It's not that they don't exist, they're just not functions, and we are usually focused on functions. So we would only usually see one y-intercept. Now zeros can happen as many times as we want and it still be a function. So that's why our zeros list might be longer, multiples of those, and why we would only see one y-intercept. Okay, other questions? All right, our second topic today is symmetry. You have three types of symmetry: x-axis, y-axis, origin. And then I want to point out that those things are not mutually exclusive, meaning if it has x-axis symmetry, it does not eliminate it from being able to have y-axis or origin. It can have more than one of those. It can have none of those. So you could have a fourth option of none. X-axis, y-axis, origin, or none. What you need to know from these is, first of all, what do they look like? X-axis symmetry means that the x-axis, this line right here, is running exactly through the middle of my picture. And that if I were to fold my picture over the x-axis, it would match up exactly with itself. To prove it, that's another thing. To verify algebraically, that is one thing I need to know. And for x-axis symmetry, I need to know how to set it up, and that is to replace all the y's in the equation with -y. Once I've done that, I'm going to clean up my equation, and I need it to equal the original. So as long as it equals the original equation, once I plug that in and clean it up, x-axis symmetry. Y-axis symmetry, same idea. Visually, the y-axis is running exactly through the middle of my picture, and if I were to fold it over my y-axis, it would match up exactly with itself. To confirm something like that algebraically, I would replace x with -x, clean it up, and I should get back exactly to the original equation. So look at those two side by side. If it has x-axis symmetry, do you notice I replaced the other letter? And if it has y-axis symmetry, I replace the other letter. So that can kind of just be like a way to remember how to do which one. If it's a x-axis or a y-axis symmetry, replace the other letter. Okay. Now origin doesn't have a letter. And so the way I remember that is because it doesn't have a letter in the title, I replace both letters. So for symmetry about the origin, to confirm it algebraically, you replace both x and y with negative x and negative y. Clean it up, and it should match the original exactly. Now, it also doesn't really have a line that draws through our picture. Instead, it's a rotation about that point. So if I leave my original up here and I take this one and I spin this one 180 degrees, what I want to show you is we get the exact same picture that we started with. Doesn't that picture look identical to that picture? Okay, that's what symmetry about the origin is. If I turn it upside down, it would match up with itself or get the exact same picture as what I started with. So again, you can have more than one of those. X-axis, y-axis, or symmetry about the origin. And you don't have to have any. They could say none at the end of that. So here's what we're going to do. Let's look at some examples. I'm going to clarify some of the directions up here. But at first it says use the graph of the equation y equals x squared plus 2 to test for symmetry with respect to the x-axis, y-axis, and origin. So when it says use the graph of the equation, that means look at the graph. Look at the graph and see visually which type of symmetry you think it has. We are not going to support our answer numerically, ever. Okay, but we are going to confirm algebraically. Now, I do want to point out, confirm algebraically is something that I expect that you can do come test time and quiz time. You guys understand what I'm saying right there? You have to be able to show those steps to confirm algebraically. So let's start with the first part. Look at the graph to decide. Visually, what are we looking at? X-axis symmetry, y-axis symmetry, origin symmetry? Y-axis. It looks like the y-axis is running right through the middle of my picture. So I think it is y-axis. That's my visual. My confirming algebraically. Remember what our rule is. If it's x-axis or y-axis, replace the other letter, right? So in the equation, if I think this is y-axis, I'm going to replace x with negative x. And then I clean it up. So this is where we're going to have a little bit of algebra reminders in our cleaning it up process. In algebra, if I have something raised to an even exponent, my resulting number will always be what kind of a number? Positive. So if it's raised to an even exponent, I have a positive number, meaning I don't need to put the negative on it anymore. If I have it raised to an even exponent, I can rewrite this as just x squared because it would be positive. Guys, you just cleaned it up. That's all you have to show. Putting in the right thing and the 1 to / maybe 2 steps to cleaning it up. Okay, so check. Does this match the original? Yeah, it does, identically, doesn't it? That's confirming that it has y-axis symmetry. We plugged in negative x, but we still got the original equation. All right, let's look at another one. Use the graph of the equation xy equals -6 to test for symmetry. So we're going to look at it, and then we're going to confirm algebraically. Okay, so on this one, does it look like the y-axis runs through the middle of my picture, and if I were to flip it over the y-axis, it would match up with itself? No? How about if I flipped it over the x-axis? Does it match up with itself? What if I spin it around the middle, halfway around? Does it match up with itself? I think so. And that's called what type of symmetry? Origin. Okay. If I want to test for origin, what am I replacing? X and y. So I'm going to take my equation. Instead of x, I write negative x. Instead of y, I write negative y. There's my setup. And my cleanup's going to take me one step. A negative times a negative is positive. So I can rewrite that as xy equals -6. And then look. It matches my original exactly. I've confirmed that it has symmetry about the origin. Questions? Okay, try this one at your table. Look at the picture, x-axis, y-axis, origin, confirm algebraically. Okay, don't be misled by what I wrote on the board. That's just some talking points here. I'm not saying that's the answer. I have not actually put my answer up on the board. What did you guys think? X-axis, y-axis, or origin? Origin. If I don't know, I can test them out algebraically. Or maybe we didn't have a picture to look at. I can test them out algebraically. I just set it up for all three. Okay, so to test out my x-axis, I plugged in negative y. Now look at the algebra for cleaning that up. I really probably want to get that y to be positive. In order to get that y to be positive, I would have divided by negative 1, right? And that would give me a positive y. And negative divided by negative would also give me a positive x cubed. Do you see how that does not match my original exactly? I just confirmed that it's not x-axis symmetry. Okay, so that one's off the table. Now, this one we need to talk about our algebra again. If I have something raised to an odd exponent, we talked even on the last page. If I have it raised to an odd exponent, it stays the same sign, right? It's not always positive, it's not always negative, it's just going to keep the same sign. So, negative x cubed is going to be negative x cubed times the negative that's in front of it would clean up to a positive x cubed. Does that match our original? No, not y-axis symmetry. On the next one, we have that same thing going on. Negative x cubed is negative x cubed times the negative in front of it is positive x cubed. And then I need to make that y positive by dividing by negative 1. And that x goes back to being a negative x cubed. Does that match our original exactly? Now, do you guys see the steps I showed right there? That's what I want to see. You knew what to plug in. It took me 2 lines. That's about the most you'll ever see. It took me 2 lines to clean it up, and it now matches the original. Questions? Last topic. Even and odd functions. Now, here's my challenge, because the testing for even and odd looks super similar to testing for x-axis, y-axis, and origin symmetry. So we need to make sure that we are taking some time to know the difference between them. When we test for even and odd, every single problem, all we are going to do is plug in negative x. Every time I test for even and odd, it does not matter which one I think it is, I plug in negative x. Okay? Now, even functions do have symmetry about the y-axis. And if they have symmetry about the y-axis, what we're going to see is when I plug in that negative x, all of the signs are going to come out to match exactly the same as the original. Odd functions have symmetry about the origin. For some reason that word got covered up, about the origin. And this is what's a little bit different than what we're used to. When I plug in negative x, what we're going to notice this time is the result that I get when I plug in negative x, all of my signs are going to flip to the exact opposite of the original. Now, if I go through, maybe I've got 3 or 4 numbers in my function. and one of them stays the same and one of them turns into the opposite and maybe the next one's opposite and the same. If I've got a combo, some of them change and some of them don't, then I would say it's neither. It doesn't have to be even or odd. Your third option is neither. Okay? So as I go through and compare my signs, if I say all of them are the same, it's even. If I say all of them are opposite, it's odd. If I've got a combo, it's neither. All right, we're ready for an example. You're going to notice a change in the directions on this one because we're not going to graph yet. You're going to do that on Monday. I know it says tomorrow. We're not coming back tomorrow. We'll do that on Monday. It says graph the function. We're going to get rid of that. We're going to do it just algebraically. We're going to do the confirm algebraically part of it today. So deciding if it's even or odd. Here's what we do. Here's my original. F of x equals x squared minus 4x plus 4. Then I'm going to do f of negative x. And we're going to compare. So all I've done is plug in negative x, and I need to clean it up. Okay, so now I'm going to clean it up. Negative x squared, again, even exponent is always going to be positive, so it would just be a positive x squared. Negative 4 times negative x would be a positive 4x, and a constant will never change. That'll stay plus 4. So if I take this one and I compare it to our original, so let me put the original right underneath of it. If I look at them sign for sign, the first sign that's in front of that x squared stayed exactly the same, right? It started out positive, stayed positive. The second sign started out negative and ended up positive, which would be opposite. And I probably could stop there because I'm not going to be the same thing all the way across, which means neither. But let's just identify the last one stayed the same. So my options are this. If every single one that I identified said the same, we would call it an even function. If every single one of them I had gone through and I identified that they were opposite of each other, I would have called it an odd function. And if I've got a combo, it's neither even or odd. So this would be neither. Questions? Okay, let's try another one. F of x equals x squared minus 4. Okay, so there's our original. I'm now going to plug in negative x, clean it up. Negative x squared is just x squared. And compare it to the original. So if I sit them side by side and go through sign for sign, I see that the first sign was positive, stayed positive. That's the same. The second sign was negative, stayed negative. That's the same. And all of my signs stayed the same all the way through. And if that's the case, which one is it? Even. So this is an even function. Questions? All right, we need one more example. Let's skip all the way to the last one. Let's go to the last example. We need one that's odd. I already told you what the answer is, but let's look at one that's odd. Okay. This is a really short one. Actually, you know what? Let's add one little sign to this. Let's change that function. Instead of f of x equals negative x cubed, let's make it negative x cubed plus x. Let's make it a little bit longer of a function so we can look at something more than just one term here. Okay, so then I plug in my negative x. I clean it up. Negative x cubed is going to be negative x cubed times the negative that was sitting out in front of it is going to become positive x cubed. And then in plus a negative x is just minus x. And I compare it to my original. So in our original, it started out negative, ended up positive. That would be the opposite signs. In the original, it started out positive, ended up negative. That would be opposite signs. And if it is opposite all the way across, it's an odd function. Any questions? All right, you guys can go ahead and get your Chromebooks out and get them up and running. You do have a homework quiz. You do not get anything for the homework quiz, so if you want to glance back at your notes, you've got about a minute or two while I get it pushed out to your computers. Your assignment will be on the board when you are done.